Okay, good evening, everyone. It's great to see such a large crowd tonight on such a rainy night. I really appreciate you coming out despite this weather. My name is Nicholas Manousis. I'm the president of the Horological Society of New York, and it's my pleasure to welcome you here to our November meeting. As usual, let's get started with a few announcements. I met a few new members before the meeting started. If there are any other new members that I did not get a chance to meet yet, please come and see me afterwards, and we'll make sure to get you your lapel pin. We really appreciate your support of the Horological Society. And before I forget, we have something that's very special, and it's for our members tonight. So if you were here at the 150th anniversary a couple years ago, you may have gotten a copy of our archival book. It's a history book about the Society. It talks about our origins going back to the 1800s in the progression to where we are today. It's a fascinating book. It was put together by our historian and archivist, Michael Asnado. So we just reprinted them, and we just received, I think, 4 boxes full of them here tonight. And so these we're giving away for free to all members. So if you're a member, that means you pay your annual dues and you have a lapel pin. This is yours for free. Just see any of the staff after the meeting, and we'll get you a copy of the book. And we sincerely thank Michael Asnado for his work in putting this together. It was a very long project, and the book is absolutely fascinating. So I think you all enjoy reading it very much. Okay, and so we have an anniversary coming up. It's the 40th anniversary of the National Watch and Clock Museum in Columbia, Pennsylvania. And so we want to wish a wonderful anniversary to our friends at the NAWCC and the museum. And they are holding an anniversary party. It is Wednesday, November 29th in the evening, and they have invited all HSNY members to come to the museum and to party with them and to check out all of the fascinating watches and clocks that are on display. It's well worth the trip. It's about a 3-hour drive from New York. If you're interested in the details, please see me after the meeting or email us, and we'll make sure to get you in touch with the National Watch and Clock Museum so you can go and partake. So again, congratulations to the NAWCC and the National Watch and Clock Museum on your 40th anniversary. So our horological education classes have been going very, very well. We're actually teaching a class right now upstairs on the 4th floor because we're here on a Tuesday night. We've been taking the classes on the road all across the country, and very pleased tonight to announce that we're going to start with a new type of class. It's a private class. So maybe you have a birthday coming up and you want to throw a birthday party for you and 5 of your closest friends and have a watchmaking class for your birthday. Or maybe you want to do some type of team building corporate retreat exercise. We can do that for you. So we can do it here at the General Society, or we can come to you. We can bring the class to you. And I'm very pleased to say that we've done 2 trial runs of this because we weren't sure how it was going to work out. So we wanted to take it easy at first. And last month we did the class at Google, and it went very, very well. So this is Vincent and Brianna over in California giving a class at Google, and so this was for Google employees, and it went very, very well. And then just last week we did a class here in New York at Bloomberg, and so there's Steve Eagle directing the class. He's actually upstairs right now directing another class. So if you have an interest in this, if you want to have a private class for your company, for your birthday, just let us know. We'd be happy to make that happen. In tonight's lecture, so I was thinking about this. I was thinking about why tonight's lecture is so important. Today, collecting vintage watches is more popular than ever, right? What do you look at when you're going to purchase a vintage watch? You look at the case, You look at the case, you see if it's been polished, if it's scratched, what's the condition of the case. Then you look at the movements. You want to make sure that the movement is running, it's ticking, and if it's ticking, how well is it keeping time? Is it regulated nicely? Have parts been replaced? Is it original? And then, of course, we look at the dial. And everyone wants to know, is the dial original? Is it what came with the watch originally? Has it been retouched at all? But there's another aspect that I think we don't pay enough attention to. Is that dial safe to handle? Is the dial radioactive? And that's exactly what we're going to look at tonight. Our speaker for the evening is the COO of the RedBar Group here in New York City and worldwide, the world-famous RedBar Group. And she is also the Director of Operations for the Horological Society of New York. Please join me in welcoming Ms. Kathleen McGivney.
Thank you, Nick. All right. So the title of my talk is How I Learned to Stop Worrying and Love Radium Dials. It's a little tongue-in-cheek, a little reference to Dr. Strangelove there. I wanted to talk about this topic because I basically started collecting watches a number of years ago and came across a radium dial watch and quickly went down a complete rabbit hole of research and learning about this watch. So I went from being, sort of a casual vintage watch collector to someone who became more than a little obsessed with radium watch dials. So I'm going to share the results of my obsession with you guys. My intention, sorry, I know I have to stand right here. My intention for this talk is to present some historical information about the use of radium in watches, why they chose to use radium in watches, and with some context about the understanding of radium safety at that time. Discuss the move to other luminous materials and the differences between them, and talk about data about the radiation levels that remain in vintage watches. I also brought my Geiger counter with me, so if any of you are wearing radium dial watches tonight, afterwards, please feel free to come up and we will test them for you. So let's go here. The background, of course, like I said, is that there's a number of radium dial watches out in the market. Many people actually seek them out and collect them and want to own radioactive watches. This is an example of one. This is a Tonic Rayville, which was sold in the United States, and you can see the paint on the hands has this sort of characteristic pockmarked look to it. You'll see some of the examples that I'm going to show you of watches that have radium dials. You can see some of the decay that happened because of the radium. So let's go into the history a little bit. What precipitated the need for luminescent watch dials? Well, like many things, necessity, breeds invention, but primarily it was for military applications. We see the beginnings of luminescent watch dials start to happen around World War I, when the military personnel needed to be able to read dials without the use of an external light source. So the origin of luminous paint in watch dials and instrument dials also came from the necessity to be able to read time at night. Why radium? So today we look back and we go, radium, well, that's radioactive, that's dangerous, why would we use that? Well, at the time, the radium was fairly newly discovered, and we'll talk a little bit about its discovery in a moment. But the process of decay that it has will basically bombards a phosphorescent material with decaying atoms, which then powers that phosphorescent material and makes it light up. So without the need for an external light source, you're getting the energy that's powering that paint and that light is coming from the atoms that you can't see. It's coming from the radium itself. So essentially the paint is not just radium, it's mixed with some other phosphorescent material that's actually doing the glowing. A sort of imperfect analogy for this is like batteries in a flashlight. You can think of the radium as the battery, it's providing the power, and you can think of the actual bulb as the thing that's the phosphorescent paint that's sort of providing the light. Radium, there's a number of isotopes, which we'll go into in a moment. It does have one specific isotope that has a half-life of 1,600 years, which is very long, which means that that longevity would allow for a paint to remain luminescent in the dark for many years without having to have an external light source power it. So that's the reason that they started using radium and experimenting with radium as a material. You'll see here, this is an ad for a radium paint, a radium luminous material called Undark. Undark was produced by the US Radium Corporation in New Jersey. You'll hear a little bit more about them shortly as well. But they would advertise this, both for manufacturers and to the general public as this sort of wonder material that shines in the dark. It allows you to be able to, read your clock dials, as you can see in the advertisement. So let's talk a little bit about radium. The discovery of radium happened in 1898. Marie Curie had already discovered and was working with uranium, and she noticed when she was working with the material that she extracted the uranium from, which is called pitchblende, that the pitchblende that was remaining after she extracted the radium was actually more radioactive than the uranium itself. So she deduced that there must be another radioactive element present. So she decided to refine the pitchblende. She experimented around with it for a little while, and it led to her discovery of both radium and polonium, the latter of which is named after her native Poland. She discovered both of those elements. Her work in this area, along with her husband Pierre, led to her being the first woman to win the Nobel Prize in Physics, along with her husband and Henri Becquerel in 1903. The Curies were the first to they coined the term radioactivity, so to describe radioactivity, so they were kind of pioneers in this field. Both of the Curies interestingly, and this kind of leads to a little bit of some later discussion, they both experienced radium burns on their skin, both accidentally while they were handling radium, and also deliberately. They would show people that this element that they held in their hand could cause actual skin burns. So they were both exposed to very extensive doses of radiation while conducting their research, because again, this was at the very beginning of the exploration and understanding of all radioactive materials just in general and how they worked. And they're really, at that time, they didn't really understand the long-term effects. This is only a handful of the isotopes of radium. It's just 4. Radium has about 33 known isotopes. These are, it's the heaviest known alkaline earth metal, and all of its isotopes are highly radioactive. So every type of radium is very radioactive. I only put 4 of them here because there are 4 that have had a lot of sort of research done about them. You'll notice that they have different half-lives. Now, half-life means that that's how long it takes for it to become about half as potent as when it was brand new. So you'll notice radium-223, half-life of a little over 11 days. A couple of them have day-long half-lives. Mesothorium, which is radium-228, which is a material that was actually used in dial paint early on. It was one of the ones that they tried using in dial paint. Has a half-life of about 5.75 years. That doesn't mean that after 5.75 years it just kind of stops glowing. That means that it's half as potent, and so there's a sort of mathematical decay rate that you could follow through this. But you'll notice that the most long-lived isotope of radium here is isotope 226. It has a half-life of 1,600 years. That means that this watch that's on my wrist that is painted with radium, isotope 226, is still radioactive because it hasn't even gotten to its half-life at this point. I put the decay modes here and the products of their decay in this chart. Don't worry, we're going to get way nerdier than this a little later on. So don't worry about that for now, but I just wanted to kind of give you a little bit of a sort of overview of the isotopes of radium, and then we'll dive pretty deep into that later on. So one of the things I want to talk about was medical uses of radium. I want to put this into context because we're looking at people using radium in dial paint on something that people are wearing on their wrists or looking at or using as a tool on an everyday basis. So I wanted to put some context into the time frame that we're looking at and people's actual understanding of the safety and efficacy of using radium for various applications. So shortly after the discovery of X-rays in the late 1800s, many medical professionals started using radiation therapy in general, X-rays in particular, to treat disease. Various forms of radiation therapy were used to treat skin conditions, such as basal cell carcinomas, lupus, and other conditions that caused skin lesions. And you see kind of historical treatments using radiation. In fact, we use radiation today to treat some cancers. So, radiation can be used as a targeted therapy in medical purposes. But at the time, it was kind of looked at as this sort of miracle cure for certain things. Even the Curies touted the medical benefits and the health benefits that could be used by using radioactive elements to treat medical conditions. Radium in particular was actually considered to have bactericidal properties, so it was used in the treatment of tuberculosis. To put it in context of the time or the early 1900s, streptomycin, which is the first effective antibiotic against tuberculosis, wasn't introduced till 1948. So people were throwing whatever they could stick at tuberculosis to try and treat people. You'll see here an example of an advertisement for radium therapy, which is, they put some radium in some water and have you ingest it. This is being said to treat things as diverse as arthritis and high blood pressure. So at this time in the early 1900s and the teens and 20s, people were using this as a therapeutic medicine. You'll also see at the same time, because radiation was found in hot spring waters that were widely touted as having healing properties, that radium baths were marketed as wonder cures for all sorts of ailments. This particular advertisement is touting their highly radioactive mineral springs, the most highly radioactive in America even. And saying that you're gonna take a cure. It says winter conditions for taking the cure. So this was in the context of what we're about to talk about in dial painting and safety. The popular understanding of radium was that it was beneficial. It's essentially the prevailing medical wisdom of the day was that small doses of radiation were either harmless or beneficial, and that large doses of radium would only have temporary effects. So that was the medical prevailing wisdom of the day. The popular wisdom was, I'm going to drink some radium and I'm going to feel great. So this is Radithor. Radithor is certified radioactive water that was sold. Again, I sort of titled this section Quackery because this was in the era where snake oil salesmen were kind of selling all kinds of stuff that really either didn't do anything to you or was actively harmful. So Radithor is a really interesting product because it was not only kind of widely used, but later on in the 30s, there was a prominent industrialist named Eben Byers who started drinking Radithor and felt a little bit better. And so he decided to drink lots and lots and lots of Radithor. And the article about his death in the paper, the headline was, "The radium water was working fine until his jaw fell off." So it is like, it was a really it's an interesting time. So people were selling all of these products out in the market. This was another product meant to restore health to everyone. This is a radioactive pad that you were supposed to wear on your back during the day and over your stomach at night, which is supposed to cure things as different as rheumatism and constipation. So this is touted to basically be a miracle cure. So there were many, many, many things like this that were on the market at the time, including water jars that you could bring to your home that had radium in them. You would fill them with water and then consume the radium to, treat your sciatica. So this was in the context of the time period that we're looking at in the early 1900s. Radium was actually a fairly, seen as beneficial. The prevailing views of safety were pretty similar to that. They thought it was beneficial. This particular product, this particular brand actually has toothpaste with radium in it and face cream with radium in it. So this, again, it was considered a beauty product. There were face creams that women would use that were supposed to make their skin, glow, which it did. So, the widespread use of radium tonics in medicine really didn't discontinue until the early 30s when, a lot of these deaths and injuries and long-term effects were really understood. My favorite one, coming up next, radium condoms. You can't really see this in the picture, but the lower part of it, it says it's for protection against disease. So if you think back to the fact that people thought that radium had bactericidal properties, it kind of makes sense, but I'm pretty sure none of you want to use these today. So this brings us to the Radium Girls. How many of you have heard of the Radium Girls? Okay. So towards the end of World War I, when demand for luminescent dials was increasing, both for military use and for popular use, because again, radium's this magic paint that can glow in the dark, many young women were hired as dial painters in factories around the US, but particularly there are 3 factories that had very heavy presence of dial painters. One was in New Jersey, one was in Connecticut, one was in Illinois. These women were all painting dials all day long with radium paint. They used a technique, they were taught to use a technique called lip pointing. So what lip pointing is, this is being demonstrated by one of the dial painters that was employed by the Radium Dial Company, I believe she's Illinois, Charlotte Purcell. She is demonstrating the technique that she was taught by all her instructors to paint the dials, which was to take the brush in your mouth and point the end of it so that you could get a finer line on the numbers that you were painting. You're thinking about the size of the dial that you're painting, you really want to get up as precise a line as possible. They were told that this paint was harmless. They were instructed to use their lips to make this point. They were actively discouraged from using a water rinse or a rag to make the point instead, because it would waste paint and it would waste time. The dial factories had a vested interest in getting as many dials painted as possible, and most of these women were paid by the piece, so they also had a vested interest in doing things as fast as possible. So the problem with that is that the body views radium as very similar to calcium. So after you ingest radium, I don't recommend it, but after you ingest radium, approximately 80% of it gets excreted via your intestines. The other 20% goes into the bloodstream. That 20% circulates around and eventually gets deposited in bone. That's because enzymes that are responsible for getting calcium out of your bloodstream and depositing it into bone see radium as a very similar compound. The enzyme thinks, I have a job to do, and it's to get calcium into the bones. That looks like calcium, and it just deposits it in the bones. So the dial painters were not only ingesting the radium via this lip pointing technique, but they were had exposure to the dust from the radium particles. So most of the paint, in fact, the vast majority of the paint was provided to them in vials as powder, and then they were mixing it with the phosphorescent material to make the actual liquid paint. So they were exposed to the dust, which they were inhaling. They were ingesting it directly by putting the brushes in their mouth. And then they were also inhaling the dust and its decay products, and we'll get, like I said, way nerdy into the decay products later, but those particulates were getting into their lungs as well. So to kind of get a little nerdy, one of radium's decay products is radon gas. Radon gas, once it gets into the air, has a very short half-life. It does a quick decay chain into a bunch of different particulates, ending in polonium-210. Polonium is really not good for you. You really don't want to have it inside your body. They're easily inhaled, the particulates, once the radon gas gets out. and it's hard to clear from the lungs, and they're very damaging. So part of the reason that I showed you the original chart about radium and its isotopes was to talk about the decay modes. We'll talk about those in a little bit. Alpha particles are fairly harmless if they're outside your body. If they're inside your body, it is not a good scene. So these are all alpha particles that we're talking about here. So these workers had been told by their employers that all of this paint was super safe, totally harmless, prevailing popular understanding of radium that it was either harmless or beneficial. Nobody really thought it was harmful except for, maybe a handful of scientists and, corporate guys. But the prevailing popular understanding was that it was beneficial. So some of the women even used the paint to paint their fingernails, their faces, their teeth, so that they would glow in the dark. And many of them it was actually known in their communities, they would walk home from work and it would start to get dark out and their dresses and skin would glow in the dark. They were, in a couple of the communities, they were called the ghost girls, which is, pretty sad if you think about what actually happened to them. So after a number of the dial painters, they started getting sick because, of course, they're consuming like this large amount of radium. They're ingesting it, they're inhaling it, and they're starting to get ill. A number of them fell ill, and they all kind of started sharing their stories with each other and realized that they had some pretty similar ailments. They were getting, some of them had, teeth, their teeth were starting to hurt. They were getting their teeth pulled and the wounds would never heal. Some of them were getting, pains in their hips or their joints, which actually turned out to be tumors eventually. So they were all getting very sick. They became convinced that these illnesses had something to do with something in their workplace. So they were being treated, the ones in New Jersey specifically were being treated by a particular dentist who also came to this conclusion and kind of ended up helping them figure out what was going on. But the medical professionals started to understand that there was something going on from their factory. In fact, one of the dental practitioners was removing a tooth for one of the dial painters, and her jaw broke off in his hand. So he took the jaw and put it in a drawer, because, like you do, and the drawer happened to have, he was a dentist, so he had X-ray film. There was a piece of X-ray film in there. And when he went back to retrieve the jaw out of the drawer a little while later, there was an image of the jaw on the film because the jaw was so radioactive that it actually left a photographic, essentially X-ray impression on the film. So the medical practitioners were like, I don't think that's normal. And so these women, all kind of trying to band together. There was some evidence, eventually this did go to trial, there was some evidence that the manufacturing companies, the scientists that were kind of high up in the manufacturing companies, as well as the people who owned these companies, knew about the dangers. In fact, the U.S. Radium Corporation, which employed all of the dial workers in New Jersey, distributed literature to the medical community about the injurious effects of radium at some point well before they, while these women were still employed and still being instructed to do lip pointing. They kept this information from the dial painters, though. So the dial painters were just doing what they were told, and they suffered very greatly. Many of them had anemia. Anemia is very common if you have radiation exposure, because bone marrow actually is way more sensitive to radiation than a lot of other parts of your body. So if it gets in your bone marrow, it can actually cause you to have anemia from that. They had bone fractures, necrosis of the jaw, and part of this was because the radium deposits in the bone would just decay the bone basically from the inside out. So these deposits of radium in their bones would just cause their bones to kind of disintegrate. One girl was walking down the street and her leg broke out from under her, broke while she was walking down the street. So many of these women suffered, very greatly. In 1927, though, Grace Fryer, who's pictured left, she was basically dying, but led a group of small group of other dial painters from the U.S. Radium Corporation in a lawsuit against them. And many of the women, died while the case was still being argued and before the case was settled. But they garnered a lot of widespread media attention. These were very sympathetic people. These were young women who, through no fault of their own, were dying in their 20s and early 30s from something that their employers had failed to keep them safe from. Some reporters even were brought to tears by the plight of these women. Some of them came to court and didn't have the strength to raise their arms to take the oath. So the dial workers eventually prevailed. They won their case. They got compensation for their medical costs, but many of them didn't live very long, and after that compensation was settled. The dial painters in Connecticut and Illinois also did end up getting compensated for their injuries. You'll see here, this is actually one of the dial painters who was giving a deposition in her home. She was too ill to actually leave her home to go to court, so the court came to her. The story of these women is actually pretty remarkable, because it's not just important in the study of the labor rights movement, which they were the first ever. They set legal precedent of being able to sue an employer for an injury incurred at work. But it was also important for the study of health physics. This, again, we have to think about the context of the time, and the people thought that radium was beneficial, and then the fact that we see that it's not. So the publicity also garnered a lot of high demand for worker safety regulations in the United States. So these women, being as brave as they were in the face of the imminent death that they knew was coming, led to occupational safety reform, which eventually culminated in the passage of OSHA in 1970. So that was the beginning of worker safety reform, was this 1927 case with these dial workers. In addition, some tissue samples and other measurements taken from dial painters, both before they died, some after they died, they exhumed their bodies, and they're still radioactive to this day. And tissue samples taken from them, including from living dial workers. So not all of the dial painters died. Many of them did and suffered greatly, but a number of them lived into their 70s, 80s, and one of them even lived to be over 100. So the ones that were living actually volunteered to be tested. So they also helped to understand the effects of radium and radiation on the human body. So the watch industry starts to change. They don't stop using radium right away. So even though these women had these very highly publicized cases about the injuries that were caused to them by radium dial paint, the watch companies were like, well, we still need to make luminescent watches, and we don't really have an alternative right now. So they changed the safety techniques. Dial painter deaths basically plummeted to zero. So they were given, dial painters continued to use radium, but they were instructed in proper safety techniques, precautions, provided with protective gear, and specifically instructed to avoid ingesting or inhaling radium. So the safety actually improved, and the industry kind of moved along. In addition, so the industry did start looking for alternate things at that time. But in addition to safety concerns, this is a close-up photo of a watch dial, this watch actually, that I'm wearing, which is one of the disadvantages to using a high energy material like radium is that the bombardment that I was talking about, where it's bombarding the phosphorescent material with decaying atoms in order to power the light, also can degrade the paint a little bit. So you see, and we'll see some other examples of this. You see in the paint here how it looks kind of pockmarked. It looks like kind of sand or like the surface of rock or something like that. That's actually due to the particles actually disintegrating the paint itself, not just the luminescent part, like the luminescence of the paint, but the paint itself. So that's a disadvantage to using something as high energy as radium, because it's like constantly just basically beating it up with radioactive decay. We also see damage to dials in some cases. There are examples of gloss dial watches that no longer have gloss on them, and that's also due to the bombardment by those decaying atoms. So the watch industry, despite deciding to use radium, found a new alternative, tritium. So they experimented a little bit with promethium, which is also has a fairly shortish half-life. It's about 17 17 and change years, but they eventually settled on tritium. This is an example of a tritium dial watch that is from the early 90s. You'll see that, obviously this is a newer watch, so it's not going to show a lot of age, but you'll see how smooth lume plots are because there's a difference in the way that tritium decays than the way that radium decays. So the emergence of tritium was for a number of reasons. One, it's considered much safer than radium because it's a gaseous radioactive isotope of hydrogen. So and then we're gonna get a little nerdy. Just warning you. It's considered less dangerous. It presents no external beta radiation threat as long as it's in a container that hydrogen cannot permeate. So if it's contained, it's not gonna, even if it's fresh, brand new tritium, it's not gonna be damaging to you. Another reason it's safer is that the dose conversion factor of radium-226 is about 3 orders of magnitude higher than tritium for ingestion. So if you were to eat tritium, again, I do not recommend, you would need to ingest about 1,000 times more tritium than radium in order to get the same effective dose. So it's a lot safer in terms of actual human dosage. This is for a couple of primary reasons. Tritium is a pure beta emitter, so radium actually sheds primarily alpha particles. There's 3 different kinds, and we will get into that I have a diagram and everything. There's 3 different kinds of radiation: alpha, beta, and gamma. Gamma is the most dangerous, but this is a pure beta emitter. Beta emitters are low energy, so it's not bombarding. It's kind of emitting, but at a lower energy. And it's also really efficiently cleared from the body when you ingest it. So you remember that if you ingest radium, about 20% of it hangs out in your body after you ingest it. Tritium, it pretty much clears out if you ingest it. So it's a lot safer for a lot of reasons. Again, I really don't recommend ingesting anything radioactive, but if you look at it from that kind of safety standpoint, that's another reason. The other advantage is it has, because it's emitting very low energy beta radiation, it's not hammering, like I said, so you see the decay of the paint doesn't really happen too much. The phosphorescence will degrade, but that's just because all phosphorescent materials eventually will stop lighting up. I'll show you a side-by-side comparison of the way that it decays. So this is a radium dial Speedmaster. This is a tritium dial Speedmaster. That one's from the 50s, and this one's from the late 60s. You can see in the decay of the paint on the radium dial watch that not only is the patina different because it's older, it's got a little bit more color to it, but you can see that it's a little harder to see on this one because it's not as pronounced, but you can see there's this little pock marking kind of going on where it looks a little sandy. And then you see the lume plots on the tritium dial watch are smooth. So this is an advantage of using tritium, is that the paint itself doesn't get kind of beaten up by its power source. So, and also, most of you know that if you're collectors of watches of this era, most tritium dial watches have a T on the dial to denote that it contains tritium. So we'll move on to modern luminous materials. So the change to modern luminescent materials, the watch industry eventually moved beyond tritium and tried to find some more modern, non-toxic luminous materials to use. Non-radioactive materials like this example of watch uses superluminova are the norm pretty much in modern watches. As you can see, it glows quite brightly once it's been lit up with a little bit of UV light. What I want to show you next is actually a little video of the current state of luminescence for a radium dial watch, a tritium dial watch, and a superluminova dial watch next to each other. So bear with me and hope this video actually loads. Yeah. Okay. So this is under UV light. You see the radium dial watch goes out immediately. Tritium dial kind of hangs on for a few seconds, and the superluminova stays lit. So the radium paint only glows when the UV light is shining on it. This is because the phosphorescent material used in the paint has essentially lost its ability to glow without an external light source directly applied to it. So this is because that bombardment that I've been talking about by the decaying radium basically wore out its ability to glow. It's like, I'm going to keep using the weak analogy of the battery and the flashlight. The battery is, in this case, is still providing power, but the bulb burned out a long time ago. So tritium watch glows for a few seconds after the UV light is removed. This is most likely because the material, the paint material, the phosphorescent paint material used is probably zinc sulfide in this particular watch. I say probably because I haven't scraped it off and tested it. But that can still be activated by sunlight. It just won't glow without an external light source to get it started, and it won't stay glowing for very long. The superluminova obviously just keeps glowing for a little bit longer. Okay. Today, most glow-in-the-dark products are made, fortunately, with non-toxic materials. One of the advantages or disadvantages, depending on who you ask, and I know some of the vintage watch collectors in this room will probably say it's a disadvantage, is that watches with non-radioactive and non-toxic paint like superluminova is that they will never change color with age, as we saw with the radium and tritium models. So you see that patina, which is very highly desired by vintage watch collectors. They want to see that patina, especially if it's even. So, you know, it's a very collectible item. Modern paint really never will age in that way. It's just going to stay the color that it was when it was painted. So some brands have taken to using paint that has an aged look to it, and as in this example of a modern Speedmaster, which is the current model, the 60th anniversary Speedmaster. Some collectors object to this, which they have coined faux patina, but some people like it as an aesthetic choice. That's just the, you know, from where we came with the watches that do actually patina. This is where we are today. So now we're going to get into the fun part. The evaluation of some radium dial watches. I recorded these as videos because doing like live overhead Geiger counter shots on here seemed like it might be a little precarious, but afterwards, if you guys would like to see the Geiger counter in action, like I said, I did bring it. So what you're about to see is going to be on this Geiger counter that we have. Radium-226, as we mentioned before, is the most commonly occurring isotope of radium, and it's also which would then make it the most commonly used isotope in radium watch dials. It has a half-life of 1,600 years. So again, these are all going to show some radiation. We should expect to see these all show some radioactive activity. We're going to be viewing measurements in counts per minute, which is over here on the left. That measures the number of atoms of a given quantity of radioactive material that the Geiger counter has detected to have decayed within 1 minute. This is specific to the instrument measuring the count, though, so it's not universally equivalent to dose rate. So you can't really like take that number and say, oh, the counts per minute look really high. Does that mean I'm going to fall over and die in 10 minutes? It's not a linear thing. It's not that simple. On the right side, we're going to look at microsieverts per hour, which measures the ionizing radiation dose that's being emitted. A sievert is basically a measure of the health effect of low-level ionizing radiation on the human body. In other words, it's a sort of a value that correlates exposure to a quantity of radiation to the risk of getting cancer. So I have this radiation dose chart here. It's also a little bit of an eye chart. This is actually like, this is only like half of the chart. So if you guys want to look at this, a friend of mine who does the comic XKCD created this after the Fukushima disaster to visually show you comparisons of doses and kind of see what your risk was. I mean, this is you know, comparing it to a nuclear disaster, which is obviously very different than a watch on your wrist, but it's a good, he's very good at putting visual things there to kind of help explain difficult to understand scientific topics. So I've made a much smaller portion of it for you to give you some examples of radiation exposure. So one measure of comparison is, this is a real thing, the banana equivalent dose. So how many of you know that bananas are naturally radioactive? Okay. Bananas contain naturally occurring radioactive isotopes, which you would know as potassium. The exposure to radiation from consuming a single banana is approximately 0.1 microsieverts, which is, a microsievert is 1/1,000,000th of a sievert, so that's really not a lot of radiation. Other examples here include, some people say 5 to 10 microsieverts from a dental X-ray, or 10 to 30 microsieverts for a single full-body CT scan. However, those last two examples are single point-in-time exposures. They're basically how much of a dose you would get for that time period, for that scan or that X-ray. What you see on the Geiger counter here is microsieverts per hour, which shows you the ionizing radiation dose per hour. But wait, there's more. I'm going to show you first a photo of the Geiger counter on a couple of different surfaces. This is background radiation. So this is just what's here out in the world where we live. The one on the left, the Geiger counter is sitting on top of a non-radioactive wooden desk. I would hope it is non-radioactive because it's my desk. And you see on the right side, it's sitting on top of a granite countertop. You'll notice that the readings are very slightly higher on the granite because granite actually has some uranium content in it. For example, the US Capitol building is constructed mainly of granite, and natural radiation levels inside the building actually approach the maximum amount per year that people are supposed to be, that it's considered safe exposure. To translate this to stochastic risk, which means the risk of cancer, if someone spent 20 years inside the Capitol building, they would incur an additional 1 in 1,000 chance of getting cancer over and above any other risk factors. So it's not really like a lot, but there's naturally occurring radium everywhere, or not radium, sorry, radiation kind of everywhere. When you take an airplane flight, you get exposed to more radiation than you do when you're standing here on the ground. Because you're closer to the sun. So, the radium is, or radiation, I'm sorry, I keep saying that. Radiation is kind of all around us, so, it's something to be aware of. All right, now we get into a video. This is the Tudor Oyster that I am wearing on my wrist right now, and we're gonna watch the video. I'm gonna let you watch it, and then I'm gonna explain it. Is it gonna play? Maybe. Oh, there we go. Okay, you see it goes from background radiation. We're right over the top of the watch. It's pinging pretty high, lots of counts per minute. But as you see, as we pull away from the watch, the counts per minute go down pretty drastically, as do the microsieverts per hour. And I'll explain why in a moment. And then we put it back down, and you see it starts to ping back down to background radiation. So we're detecting quite a bit of radioactive decay. But there's a couple of reasons why we're seeing so much of that. One is that we're sitting right on top of the front of the crystal. So we're very, very close to the radiation source. The Geiger counter is showing about 110-ish thousand atoms detected to have decayed per minute. But you see from the length of the video is less than a minute. It's calculating that based on its point-in-time calculations. This is the number of events detected, but it doesn't necessarily correlate to the actual disintegration rate, as there are a number of factors such as distance that come into play. As I mentioned, you see when we move the Geiger counter away from the watch, the distance, the air and particles and whatever that's in between the Geiger counter and the watch will actually kind of minimize how much exposure we're getting. We see that the microsievert count is about 320. There we go. So we see like 110,000 here. We see the microsievert count is about 320 microsieverts per hour. Single whole body CT scan, 10 to 30 millisieverts. I'm sorry, I misspoke that earlier. So one might conclude that this hourly emission rate would be like getting a CT scan every 4 days or so, which is actually not true. Keep in mind, this is a very small contained space. We have the Geiger counter directly on top of the watch, and you're not getting whole body exposure from this. you're not getting a CT scan. You're not a nuclear worker. You're not getting whole body exposure here. So you'll notice that when the radium-226 decay is almost all alpha particles. Alpha radiation only has a range of a few centimeters in the air. So distance from a radiation source and the absorption or scattering of particles such as air or metal in between the source and the detector are considerations in determining actual counting efficiency and actual dose to the human body. So this is a chart that's probably hard to read on here, but what it's trying to say here is that you have to look at the counts, the dose, and then figure out the distance and the transmission factors there in order to actually translate that Geiger counter reading into something that actually is equivalent to the physical dose of radiation that you're getting. This video is going to demonstrate that a little bit more. So this is from the back of the same watch. So we see it turn it over, it's the same watch. Apologies for the flickering of the screen. We had a little bit of a funky rate there, but you see how much less, how many fewer counts and how many fewer microsieverts per hour are happening here? That's because alpha particles can't penetrate so much as this piece of paper. Steel in between the radium and the Geiger counter actually blocks almost all of that. It's blocking. The reason we're still seeing some disintegration is because there's a little tiny bit of gamma decay in radium decay. So we'll look, I think the next slide has a photo maybe. So this is a dial. This is another point in time. The readings go up and down, especially with regards to counts per minute when you're looking at this. This is a dial in the case back. You see that the microsieverts per hour go from 346 to 2.4. That's pretty significant, and that's because of the steel. Just by placing some steel between the radium and the Geiger counter, you see that drop. To put this into perspective, 2.4 microsieverts per hour is roughly equivalent to your hourly whole body exposure at airline cruise altitude. So the back of your, the point, this is, that's really not a lot of actual radiation. It's a small contained point of exposure. It's not whole body radiation. And almost all of the particles emitted by radium-226 are alpha. Some of its decay products emit beta particles. So the decay products, including radon gas, emit beta particles as part of their decay. And then the radium-226 decays with gamma about 3.5% of the time. So that's why we still see a little bit of elevated readings, but you know, it really dramatically drops. This is where I was talking about. I have a chart to demonstrate. The alpha radiation, alpha particles, again, like I said, are really not so dangerous to you when they're outside your body. They don't penetrate your skin. So they can be stopped by, like I said, a piece of paper. You can toss, you know, your wallet on top of it, and they'll be stopped by it. Alpha radiation, you know, is definitely a concern if you've ingested or inhaled it. Beta radiation can usually penetrate a little bit further, maybe a couple millimeters into the skin, but it depends on the source of the beta radiation, whether it's a gas, whether it's low energy, et cetera, but can be stopped by aluminum foil. So you can, if you have a radioactive watch, you can just pop it in a box and line it with aluminum foil, and you put a Geiger counter outside that box, and it won't see anything. Gamma is where we're seeing, you know, penetration, and that's what we would be concerned about with regards to radioactive safety, but that can be stopped by lead. So I'm going to show you a couple more videos, a couple more watches. This watch is a universal Geneve Polerouter. It doesn't even really look like it has radium on the dial. Pretty, like, so you see there's a lot of counts, but the microsieverts per hour is actually a lot lower than the first watch. Again, I'm sorry for the flickering in the screen there, but he's gonna put it back on the back of the watch, and you can see it's significantly lower with the counts per minute and the microsieverts per hour. Another thing to note here when you're using a Geiger counter is that a Geiger counter needs to be calibrated for a source. So it needs to be calibrated for a specific material and can generally only be considered totally accurate for that source. Unless you specifically go get a medical or scientific grade Geiger counter and specifically request that it be calibrated to the material you're testing, in this case, radium-226, the dose rate reading can be helpful qualitative measurement to like compare objects. So I can say like, this object clearly has radium, this object clearly has radium, but it shouldn't be used quantitatively in this context as far as calculating dose. Pretty much every commercially available Geiger counter is calibrated to cesium-137, which is primarily a gamma emitter, and it's, I'll talk about this a little later, but these are mostly used for environmental purposes to find out if this room has radiation in it, not if a watch does. So, they're calculated to cesium-137, usually at a specific geometry and a specific distance, and so would be useful for calculating external exposure to gamma, but not necessarily as useful for calculating dose in this case. There's another video that we can show you. This is an Ed White Speedy. Pretty high on counts per minute and pretty high on microsieverts per hour. So definitely radium. Right. And then we'll go with a tritium dial Speedmaster just to show you that it does not really emit much more than background radiation. So tritium has a much shorter half-life, so this is what we would expect to see. It's basically about the same as background radiation, because most of this tritium dial Speedmaster is old enough that the tritium would have already completely discharged. Yes, thank you. Oops, that is not where I wanted to go. There we go. This is a group of radium dial watches, just a pretty picture for you guys. You see they all look very different. They're all from very different time periods. My husband has the one on the left on his wrist today. If you guys want to look at it, it's an old pocket watch that was converted to a wristwatch, probably circa World War I-ish. So it's pretty neat. Okay, so what are these implications here? I want to note that my Geiger counter that I'm showing you this on is, like most commercially available Geiger counters, is calibrated to cesium-137. So that it is calibrated to a particular substance that emits primarily gamma radiation. However, it, unlike most commercially available Geiger counters, has a pancake sensor that is capable of detecting alpha and beta. So I can use it in the is it radium test. Right? A lot of other Geiger counters cannot be used for that because they don't measure alpha or beta at all. There's really nothing wrong with that. You can go out and buy a Geiger counter and go to Fukushima and walk around and see what parts of the area are contaminated. But if you want to find out, about if a surface is contaminated, it's a lot better if you have something that can ping on both, that can understand and read alpha and beta as well, because gamma rays can travel really long distances and it's really hard to pinpoint where they come from. So a counter's ability to detect alpha and beta is actually really helpful. All right, so the implications for collectors and watchmakers. One that comes up kind of often and really interestingly online and amongst collectors is to whether a Geiger counter can be used or is a useful tool in the authentication of a watch. Lots and lots of arguments have been had on the internet about this. If a watch is from, say, I don't know, 1945 and is known to have radium paint, do you think that you can reliably find a Geiger counter that will tell you an exact fixed amount of counts per minute and microsieverts per hour to assure you that you're getting the real thing? The short answer is no. The longer answer can get a little complicated. There are a number of factors that can be used. You see, this is the same watch, or no, that's not the same watch, but you saw this watch in the previous video. Counts per minute were pretty high, and the microsieverts per hour were over 320. This particular Geiger counter only goes up to 9.99. It doesn't even go to 11. That's where it stops. That's as high as it'll tell you. So it's only measuring, I would assume it's only measuring gamma radiation, but I don't know what specific sensor is in here. So there's lots of factors that can contribute to a reading that you might not expect from a watch. So if you're using this as a authenticity mechanism, you should keep this in mind. Radium decay rate is predictable. Specifically for radium-226, it's got a very long half-life. It's easy to do the math if you're a physicist. But you could probably calculate the age using a Geiger counter and some math. However, but that doesn't tell us the whole story. So you could have a number of factors that are affecting the readings from your watch. Again, not least being the Geiger counter itself. What type of sensor is it using? Can it detect alpha and beta radiation? That's fine for general purposes if you have a gamma-only detector, but it doesn't help us much when we're dealing with a substance like radium that's primarily an alpha emitter, or tritium, which just emits beta. If you have a Geiger counter that only measures gamma, you're not going to get anything off of a tritium watch, even if it's like fresh tritium out of the box. Additionally, you have to think about when watch parts were manufactured, the dials were painted in a different place than hands were done, and movements were made in a different place. So the time periods at which these things were made, when the paint was made, all of these things could be done at different times. So your case might be from 1945, but your paint might be from 1935. The paint formulations could be a factor, especially when the industry was experimenting with different kinds of paint formulations. After the radium girls and their plight, the industry was experimenting with all kinds of stuff, and you don't know if there's a little bit of radium and there's a little bit of tritium. There's a lot of other factors that could go into that. There could be radioluminescent substances such as mesothorium, which is radium isotope 228, which has a half-life of 5.75 years. Promethium, which was briefly toyed with in the era right before tritium, with a half-life of about 17.7 years, and tritium, which has a half-life of about 12.3, 12.5 years. If these watches were ever serviced, they ever had the movements cleaned, the amount of radium present could be different, or paint replacement. I mean, there's tons and tons of different factors that could go into this. So if there was a problem with the gasket, like while you're testing the watch, and there's radon gas escaping, that could affect the reading. So there's a number of factors that can go into that. So, and not to make collectors paranoid, but if someone went out and got some old vials of radium paint powder, and they could paint anything with this paint, and you could hold a Geiger counter over it, and it would look like it was as old as however old this paint is. I mean, watchmakers' estates come up every so often. They might have old vials of radium paint in their bench. So, should you use a Geiger counter as a data point when determining authenticity? Sure, but should you use it as a sole determining factor for authenticity? Absolutely not. Since the only way to know for sure what particular radioactive substance is what it is on the dial is to sample it, and that would damage the paint on a dial, which no vintage collector wants. We have to use some deductive reasoning here. We know that radium-226 was used in watch dials, and it has a long half-life. We know that the other radioactive substances that were used in watch dials have half-lives that would render them pretty much background at this point. So it's pretty safe to assume that if Geiger counter is pinging with anything, that there's some radium present. And it's probably radium-226, unless someone's mixing up fresh batches of radium paint somewhere in the basement. Beyond that, the Geiger counter can't tell us much more. It is a blunt instrument. It's quite frankly not geared towards this purpose. It's useful for us, in this particular Geiger counter is useful for us because it detects alpha radiation, but it's meant to measure radiation in a larger environment to gauge whole body exposure and danger towards humans, not as a fine point measure of authenticity for an item we're trying to pinpoint down to a specific date. So, from a safety standpoint, individual collectors should just consider the data and exercise their own judgment. As you may have noticed, I'm a little fascinated with this topic. I own and regularly handle several radium dial watches, which are all up here if you'd like to have a look. But I store them in a lead-lined pouch, which I also have here with me today when I'm storing them in my house. I have cats. I don't want, what if they eat the watch? I don't know. So I can't tell you what decision to make. You should evaluate the potential risks for yourself and make an educated choice. Should you use a Geiger counter as a data point to help you evaluate risk? Sure. Take the readings with a grain of non-radium salt, though. I had to. Radium salts, it's funny. Even this specific Geiger counter, again, which uses this pancake sensor, is going to overestimate your dose because I'm standing here with the sensor right on top of the watch. Especially if you're putting it right on top of whatever the radiation source is, since they're mostly emitting alpha. This watch dial is mostly emitting alpha particles. As soon as I raise it away, the air and all of that stuff is going to interfere. They don't travel far in the air. 1 count of gamma radiation doesn't have the same biological impact as 1 count of alpha or 1 count of beta either. So if you're seeing high counts per minute and it's alpha radiation, as long as it's outside your body, like it's really not as bad as it looks. It was very dramatic on the video, but to be able to use this kind of detector for a close-up measure of a radiation dose, you would need an energy compensator. What an energy compensator is essentially a piece of plastic. It's a very expensive, very highly calibrated piece of plastic that that approximates your body's tissue and kind of covers the sensor, so that the only radiation that would be actually reaching the sensor would be gamma radiation. So that's the only real way to tell like actual human body dose and risk to your flesh. So this is the lead bag. It's a repurposed film bag which protected film. Do you remember film from X-rays? And so it actually fits watches really quite nicely. Watchmakers, on the other hand, should exercise some caution when servicing a watch that contains radium. Since radium-226 emits, again, mostly alpha radiation, ingestion and inhalation are really the primary causes of health concern. However, modern watchmakers are not like the radium girls. They're not going to be ingesting and inhaling all of the time. So you're not going to be probably ingesting or inhaling very large quantities of this substance. But you should take some precautions when servicing watches. Use some finger cots, maybe a mask. A safety tip that I got from my physicist friend for working with radium is to work in a very well ventilated area, preferably with a small fan blowing away from your face across the surface of the watch. You definitely don't want the fan pointed at your face. Radon, which is a decay product of radium, is a noble gas. It's very mobile in the air, and it's not really dangerous until it decays and you get the particulates in your lung. We talked about those before. Some of the decay products decay into these wonderful particulates, and I will show you this beautiful radon decay chart. You can see some of the decay rates. So as radon decays, it stays as radon-222. This is a daughter element. It's a decay product of radium for about a little under 4 days. And then it goes to polonium-218, which takes 3.1 minutes to decay. So you can see this is like 27 minutes, 20 minutes, 160 microseconds. And then we get down to lead-210. So which is a little longer, 22 years. But this decay chain right here, those are the particulates you don't want to have in your lungs. So if you're a watchmaker and you're working with a radioactive watch, a watch with radium on the dial, you just take those precautions and use a well-ventilated area. My physicist who actually handles radioactive products said working in a well-ventilated area will mitigate the risk. If you think about it, it's basically in this context, if you hear of a home with a radon mitigation system, it's just like a big fan that circulates air out of the basement, which is where radon would normally collect if you had a house with a basement. So in conclusion, this is the back of the Tornik Rayvel watch that we saw at the very beginning. The history of the use of radium in watches is really more than just some radioactive paint on a dial or a period of time when we were kind of doing a lot of things with industrial products and maybe not testing them before before we utilize them in mass production. It encompasses scientific discovery, industrial innovation, worker health impact, corporate cover-ups, courageous women fighting for their lives, and one of the earliest cases of worker injury leading to workplace safety reform. It's kind of a big deal. When you look at a watch, I encourage you guys, when you look at watches with radium paint on the dial, I hope you can see that it's more than just a watch. There's a whole story there. It's a piece of history. Thank you. One more thing to say real quick. Before we move to Q&A, I want to extend some special thanks to the folks on this slide, some of whom lent me their watches to photograph, one of whom is my wonderful husband, who took most of these fantastic macro photos of the watches, including this really great radium dial pocket watch that was converted to a wristwatch, and Lisa Manglass, who provided invaluable help with kind of checking my work on the physics explanations. So thank you.
All right. Any questions for Kathleen? Please raise your hand, and I will bring the microphone to you.
A slight concern, since I just had a full-body CAT scan. Did they say that the radiation, right, like calcium, gets absorbed in the structure in the bones? How long does the radiation stay in your bones? Did anybody tell you anything?
Yeah,
about
that's
that?
if you ingest it. So having a CAT scan is actually, I forget what the max safe dose, but you can have like 3 or 4 CAT scans a year and you're fine. It's not going to stay in your bones if you
And
just
their
have-
long-term effects have been studied, and they
Yep,
beautiful.
absolutely. Yeah.
In class, in watchmaking class, what they had us do was under running water, use a wood peg to take the radioactive material off.
Yep.
So you didn't have to breathe it in.
Yeah, absolutely. If that is a good point. If you are removing radioactive paint, if you're removing radium paint, running it underwater will prevent the particles from dissipating in the air, and that whole decay process with the chart you won't see that because the radon's not escaping into the air.
A wonderful lecture. Thank you.
Thank you.
When I work on radium watches, what I do is I make sure that the dust, when you open up the watch, that you're carefully, I usually do it outside, so that there's enough air, and of course, I make sure that I'm not near the dust. You don't want to open it up inside the house, especially if you're doing restoration work, because it's accumulative.
Yep,
And
absolutely.
of course, the danger is not from the radiation from the watch itself, but it's ingesting the radiation.
Yep, exactly. It's the dust is really the biggest health concern there. The dust and the decay products from the gas that radium emits.
Usually, doing hands, I scrape it off with water, right?
Yeah, underwater though. Yeah.
It's actually under running water, and I let the particles lay down, and then I seal them in some type of container. I have a small container where I put the dust particles.
That's a good practice. Yeah.
All I do hazmat.
Yeah. Well, that's good. If you have hazmat training, then you definitely know what to do.
How bright is the radium dial if it was new today?
That's interesting because I've never seen or handled a brand new radium dial, so I really don't know the answer to that question. But that's an interesting question. I'm sure that there's if there's radium paint out there that people want it, I wouldn't experiment with it. But yeah, I'm sure there's ways to find out. I'm sure there's images out there too that people have taken at some point in the past with the glow. But the interesting thing about it is that it would glow without any sort of external light source. So it'd be pitch dark and you could read your watch. So it's kind of cool, but it's a little dangerous.
Kathleen, when and why did you start this research?
So I came across a radium dial watch that someone brought to RedBar that had a burn on it. So the watch was probably, I don't know, I think it was from the 40s or the 50s, and I don't think the hands had moved on it in years, as if someone had just chucked it in a drawer, and it had sat in the same, with the hand in the same position, the minute hand in the same position, and it left a burn mark on the dial because the radium in the paint on the hand had basically, again, done that bombarding thing and left this burn mark. So I was like, that's interesting, and and I started doing research on radium burns on dials, and then came across the Radium Girls and their tragic story, and then I just went down a whole rabbit hole of trying to understand, what are their implications? Because I know so many people that own vintage watches, and I wanted to know if there were, any safety implications. for myself or for my friends or for my watchmaker friends that that were there. But then I also just got really interested in the history and the context when I was doing the research on my own. Kind of a while ago, I started doing this. I was going to do it as an article, and then thought it would made better sense as a talk. But I started doing research as an article, and then I really the stuff about the like early teens and 20s and like all the snake oil and quackery and stuff that kind of went on at that time, not just with radium, but with all kinds of the miracle cures that like people were hawking at the state fair and that kind of stuff, totally fascinates me anyway. So going down that road, really, it just was a fascinating topic to me. So that's how I started.
Any other questions for Kathleen?
Hi. First of all, thank you very much for everything. This has been great. On a practical level, is it really that big of a deal to be cautious, going home, looking at our watches, and maybe taking a new approach on how we're handling these watches?
So I on a practical level, for myself, and this is again, I say for my own personal decision, I think that the risks are low enough that I regularly handle the watches. Many people take an approach that any radioactive exposure at all is a risk of cancer. That's really more of a like scientific lab kind of approach where there's like a zero tolerance kind of approach to that. On a practical level, if you're not opening the watch up, you're not, laying it across your mucous membranes on a regular basis, you're not ingesting anything from it. On a practical level, for me personally, my risk tolerance allows for handling and owning these watches.
Thank you.
Sure.
Only some medical notice on your lecture. It was a beautiful lecture, but radium-223 is now used in oncology for
Yep.
treatment of prostate cancer, alpha-radin.
Yep.
Name is alpha-radin, and this is FDA approved.
Yep. Yeah, so there are
Drug.
medical uses of various radioactive materials. There's some people people do targeted radiation therapy for cancerous tumors. You're right, there is radium-223 as a medicine now. So there are newer uses and continued uses of, people still use x-rays to do diagnostics. So there's, CT scans are a diagnostic procedure. They all have some sort of radioactive component to them. So yeah, it's not that we've gone from using radium in medicine to not using it at all, but rather we've gone to a much more informed way of using radium without incurring as many of the dangers. Yeah. Yeah, exactly. Yeah, exactly. Yeah. Yep, exactly.
Any other questions for Kathleen? All right, let's give her another hand. Okay, so before we part ways tonight, Q&A, I just wanted to make a special announcement. Please mark it on your calendars, and hope to see everyone back here in December. So December 4th, we have a special event with a very special lecturer making the trip across the Atlantic Ocean from the Isle of Man, Mr. Roger Smith. So this is going to be a ticketed event, and it's going to be a lot of fun. We hope to see everyone there, and watch for more details on this event coming soon. Thank you, everyone. Thank you, Kathleen. Have a great night.